Actually, a step one question from 2010, question number 13 about Poisson distribution, because that's now been moved into step two. It's question 5 from the step two stats support module. Let's do it straight away. So we've got George receiving some text via a Poisson distribution with mean lambda. So okay, that's fine. To wait between 1 and 2 hours in the morning before he receives his first text, that means that he must get no text in the first hour and then at least one text in the second. So, okay, well, the probability of getting no text in the first hour is a Poisson distribution, right? So it's going to be, so this is probability of no text in the first hour, and then, of course, times, because we need them both to happen, probability of at least one in the second. Now, we can't actually work out the probability of this very easily, so we're just going to do 1 minus the probability of x less than 1, which is the same as the probability of x equaling 0, of course. We could expand this now, or we could just substitute in the values. So, of course, for a Poisson distribution, it's, what is it, e to the lambda times lambda to the n over n factorial. But n is just 0 in both those cases, which makes the lambda to the n and the n factorial go away. So it just becomes e to the minus lambda each time. Hopefully I said minus lambda first. Maybe I didn't. Anyway, e to the minus lambda at the top there. Of course, now we expand this out. Well, we're told actually this equals p, which is very useful. Now we can expand that out. And when we do some timesing by e to the 2 lambda on both sides and rearrange, we'll end up with what they want us to get. Given that 4p is less than 1, show that there are 2 values for which lambda satisfies this. Well, this is an equation. It's a quadratic equation, right? Because it's e to the lambda squared here and e to the lambda here. So this is a quadratic equation with a equal to p, b equal to -1, and c equal to 1. So we can just use the quadratic formula with e to the lambda as our chosen kind of variable that's being built, that the quadratic is built from. So we just shove it right there. And we want this to be a few things, right? So we need it to be real. So that means we need 1 minus 4p to be greater than 0, which we're obviously going to get because it tells us that this is true. So that's fine. That's consistent. So we're going to get that. What else do we need? Well, we also need e to the lambda. Lambda is a positive number, right? Because you can't receive minus text. So lambda is a positive number. E to a positive number is bigger than 1. So we also need both of these two answers to be bigger than 1. So, okay, that means we need 1 plus this over this to be bigger than 1, which we'll assess first. And we also need 1 minus this over this to be bigger than 1. Let's do this one first. There's a few things you could do here. P is positive because it's a probability. So we can times by 2p safely here. And you can do some rearranging and squaring if you want. The quickest thing to notice is that this side over here is definitely bigger than 1 because it's 1 plus something. So this is bigger than 1. Because p is less than a quarter, this here is definitely less than a half, or at the very least less than 1. So of course this is fine. So okay, we're all good to go. So that one's all done. So now we assess the negative solution and show that's also bigger than 1. Again, we can safely times by 2p. We are going to rearrange and square both sides here. Now, because this is definitely positive, because again 2p is definitely less than 1, and because p is less than a quarter, so that's all fine. This is also positive, so we can square this kind of safely, square that out, do some rearranging, and you get this. This is always true. And so we are always going to have these 2 positive values. That's absolutely fine. The number of texts that this person receives on 2 phones can be done by this. So at some point you should be thinking here that you're going to have x twiddles po lambda 1, x, y twiddles po lambda 2. You're going to combine them at some point. That combines to make something like z twiddles po lambda 1 plus lambda 2, right? You're just allowed to add the means there when you're combining them. Now, we're not going to do that yet because it tells us that the probability of doing this with each of our phones is also p. So that means lambda 1 is a solution to this equation because this equation was setting this probability of p. And lambda 2 is also a solution to this. But we just found out that there are 2 solutions to this. They were this, and they're both fine. So that means lambda 1 must be one of them and lambda 2 the other. So let's just set that. It doesn't matter which way around we do it. It's tempting to add these things together because you get e to the lambda 1 plus e to the lambda 2 equals 1 over 2p plus 1 over 2p because these things cancel immediately if you add them together. But that doesn't actually help you because there's not really an easy way to sort out e to the lambda 1 plus e to the lambda 2. So instead you times them together. And if we times them together, when we expand this out, of course, because it's like a conjugate pair, some really good stuff happens here. The 1's cancel, the 4p's will then cancel, and you just end up with 1 over p, which is fantastic. Because that means, of course, taking log of both sides, we can end up with this, which is what they wanted us there. Find the probabilities now in terms of p that she waits between 1 and 2 hours to receive a text, like on the combined phone scale. So this is what I was saying, was if we have these 2 Poisson distributions, if we're thinking of both phones at the same time, we can just create this distribution to describe how often we get texts, thinking of both phones as kind of the same singular phone. So, okay, well, that's all fine. So what we'll do, of course, we know because they prepped us for this, lambda 1 plus lambda 2 is this thing here. And we can just do the same thing we did at the very start, which is we need 0 techs in the first hour, and then we also need at least 1 tex in the second. That's the same as 1 minus no techs. P of z equals 0 is, again, e to the minus lambda times lambda to the n, but n is 0, so that goes away, over n factorial, n is 0, so that goes away. So this just turns out to be e to the minus lambda again. But that's e to the minus log 1 over p, and likewise this one here. But this is log of p to the minus 1, and then the minus 1 comes down, and it cancels with that minus, and you just get log p. E to the log, it cancels, you get p, and you end up with this, and that's the whole question done. Thanks for watching.